Welcome to G4 Lab. This is our first video covering IB Computer Science Topic 4, and we are covering Part 1, Computational Thinking and Program Design in this video. So here's an overview of the IB Computer Science Paper 1 syllabus. The core syllabus content consists of both SL and HL listed out here. So if you are only an SL student, then you will only be covering topics 1 to 4, whereas if you're an HL student, you'll be covering topics from 1 to 7. And we will be focusing on topic 4, computational thinking, problem solving, and programming first. So why would we start with topic 4 instead of topic 1? Well, topic 4 focuses on practical code instead of theoretical concepts. It gives coding background early on for IA topic brainstorming. And topic 4 is also the largest and the most heavily weighted of the 7 paper 1 topics. We will return to topics 1 to 3 once we have established a strong programming base. So, our first topic is computational thinking. Computational thinking is a problem-solving method that involves breaking down complex problems into smaller parts to find solutions using algorithms. The IB course requires that you learn and understand the following 6 prompts to help you solve problems while thinking and programming. The first of these is thinking procedurally, and then thinking logically, thinking abstractly, thinking ahead, thinking concurrently, and thinking recursively. I'll go more into depth in the later slides. So the first type of thinking is thinking procedurally. Thinking procedurally refers to dividing a problem into reproducible parts that, if correctly followed, will generate a solution every single time. Each step may and can be further divided into their own subparts. So the keyword here is reproducible. So some of you who've taken maybe Intro to Computer Science might remember this as an exercise, but you would have to write a series of instructions for an algorithm, and this series of instructions would be followed by another person, and you would try to produce the same output as you did. So the real-world computing example of this is functions, and in a real-world example, something like a recipe for a meal. Think about it like if I'm making pasta, for example, I have to divide it and into different parts. What do I put in first? Should I make the noodles first? Do I buy it from the grocery store? So these steps have to be followed in order to reproduce the parts that can be followed every single time. Second thinking is logically. Thinking logically is all about making decisions and forming the conditions that will affect those decisions. There are generally 3 steps. Number 1, identify when decision making is required. Number 2, identify what is the decision that needs to be made. And number 3, identify the conditions which will form the basis of each decision. The computing example is conditional statements, something like if-else, while statements. And real-world example of this is deciding what to wear based on your temperature, because let's say if we were transferred into this something like pseudocode, it would be like if the weather is 90 degrees Fahrenheit plus, more than that, then I would wear shorts and a t-shirt, and if it's below that, you would wear something else, etc. The third type of thinking is thinking abstractly, being able to create a meaningful model or way to represent a real-world thing in a way that contains everything that is relevant and nothing that isn't. So abstraction, the term abstraction means ignoring irrelevant details to focus on essential aspects. So when you take a real-world situation and you're writing a program or an algorithm, you're creating an abstraction. It's a way to represent the situation within the computer. So if you think about it, everything you do in IB Computer Science or just programming outside of the classroom, it is a type of abstraction because you're writing it inside the computer, and the computer itself is an abstraction as well. You're only looking at the screen, and you don't have to worry about whatever's under the circuits, the hardware. So a lot of things can be abstractions. One example of this, I'm sure a lot of people have experience with, is Scratch. This block coding in Scratch is a type of abstraction because you don't have to look and you don't have to write the actual code for it. You just drag and drop the code, and it's a way of simplifying programming to teach it to younger audiences or beginners. And a computer example of this are classes, variables, and data structures. All of these can be used to make up an abstraction, a type of program, something that solves a problem in a way where the user doesn't have to look into the irrelevant aspects. So something like a variable, I'm setting this variable to a numbered value. I don't exactly care about what the value is, but when it's inside a variable, I'm using that to solve my algorithm. Thinking ahead. Thinking ahead means pre-planning and attempting to anticipate future needs. This is very important for program design because here's the steps. Like, what are the preconditions to solving the problem? What are the post conditions? And you want to anticipate the exceptions to the rule. So for preconditions, you have to think about what has to be in place or known in order to be able to solve the problem. So that means, what are the inputs going to be? And for post conditions, what will be in place after the problem has been correctly solved, or in other words, what are the outputs going to be? And for anticipating exceptions to the rule, what are the likely exceptions that we're going to need to deal with? How will we want to handle them? This can include some things like edge cases and testing. Something like input validation is a type of testing. And a real world example is grocery shopping lists. You're thinking ahead of what you are going to need to cook, and you're creating a list. So that is a type of thinking ahead. And we also have thinking concurrently. Concurrency deals with multiple things happening at the same time. This includes a computing problem that involves multiple threads running simultaneously. So an example of this is a construction project. In a construction project, multiple things are happening. You're not just someone's operating the crane, someone is laying the foundation, someone's building the scaffolding. So it's not just one thing, it's multiple things happening at the same time. And in computing, something like GPUs in a computer allow the computer to do multiple things and run multiple things at the same time. And we use multi-threading in computing to run multiple things at the same time in your program. So one important thing to know is you will not be required to construct a concurrent processing in IBCS, but you may be required to identify, interpret, and understand one. So you don't have to know how to build one, you just have to recognize one. Thinking recursively. So recursion is the breaking down of a complex problem into smaller parts and solving each part after the other until solved. This is considered to be one of the hardest topics in IBCS, and since it's technically an HL only topic that is covered more in depth in topic 5, we'll be saving this topic until then. So for now, you don't have to know recursion. So another way to think about this is the 4-step computational thinking approach. A lot of teachers actually prefer this method than the IB's 6 prompts. But the 4-step computational thinking approach is basically, step 1 is decomposition. You have to ask yourself, can I divide this into subproblems? Number 2 is pattern recognition. Can I find repeating patterns? And number 3 is abstraction. Can I generalize this to make an overall rule? And 4 is algorithm design. Can I design the programming steps for any of this? And now we'll look at an example. Okay, so apply the four-step approach to solve this problem by sorting. Right here we have an unsorted list and we want to sort it into ascending order. So like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So applying the four-step approach, number one, decomposition. Can we divide this into multiple subproblems? So right here, for example, we're looking through number one, step one. We go through the list, we're finding the number one, and we're adding it to our sorted list. Step two, finding the number two, add it to our sorted list. Step three, find three, add it to our sorted list. Okay. The second step is pattern recognition. Can I find repeating patterns in this sorting problem? So what I just did right here, this is repeated for the entire list until we get our sorted list. So the pattern here is we're looking through the list and we're finding the next number and we're putting it into a sorted list. So how would we write this into pseudocode? So for example, number one, find one, move to sorted list. Number two, find two, move into sorted list. Number three, find three, moving into a sorted list. So right now we're already using pattern recognition. But how can we apply abstraction, which is the next step to this? Well, if you're looking at this, we're finding 1, 2, and 3. We don't really have to know that we're finding which specific number. So if we remove all of the find 1, 2, and 3, what do we get? We get a simpler instruction. For example, number one, search through the values. Search values, find lowest, because that is basically what we're doing. Find lowest, and after that, move to sorted list. So basically what we're doing here is we're searching through the values. We're 6, 4, 3, 12, 7, 8, 2, 11, blah, 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 and oh, we find 1. This is the lowest number out of all of them. We're moving this to a sorted list, and then after this 1 is gone, we removed it from the original, and we're searching through again, and we're finding 2, remove number 2, searching through again, find 3, remove, add here, and that's basically what we're doing. Now the fourth step is algorithm design. Can I design programming steps for this? So I'm not actually going to go through the exact code we need to do this, because we'll cover that later. The actual sorting algorithms will be covered in our next video when we're talking about standard algorithms. But if we were to write this in sort of pseudocode-esque things, it would go something like this. So we have a precondition that while unsorted values remain. So let's say we sort through all of them and there's nothing left. How does the program know to stop sorting? Well, it'll stop sorting when when all of them are sorted. You want to stop the program. So you want a while conditional. And inside that while loop, search through the values. Exactly what we talked about later, abstraction. Second step, find lowest. Third step, move to sorted. So in algorithm design, it's important to think about edge cases, what's going to happen when we stop the program, what things might make it break. So you have to add this condition, or else the program never stops, basically. And if you've learned Java before, you'll know that if it goes out of bounds, then it'll throw in an out of bounds exception. Okay. So now that we've covered all computational thinking, we can go on to program design. So program design is all about solving problems. If you can't solve and articulate the problem by hand, you can't solve it with code. So this is more of the logic part. There's three key strategies you should be familiar with when articulating and testing algorithms. There are pseudocode, flowcharts, and trace tables. I'm sure a lot of people, many of you probably already familiar with pseudocode, so quickly go through that. Pseudocode is basically structured English. It's intended to communicate an algorithm to other programmers or to yourself, regardless of the programming language. So pseudocode is not language specific. So please note, this course requires you to be able to create as well as interpret and analyze pseudocode. So this is a really important part of IBCS. So since provided that examiners can see the logic in a candidate's response, regardless of language, it will be credited. No marks will be withheld for syntax errors. That's one of the nice things about IB. So since there's no fixed syntax, you can just use pseudocode. But however, IB has specific grammar that will use to ask you questions in pseudocode. So although you can use whatever syntax you want when you're writing the pseudocode, as long as it's comprehensible and it makes sense, they'll ask you questions in pseudocode are adhering to a certain grammar. So although you're not obligated to follow their syntax in your response, you won't lose credit for doing so. But you should be familiar enough with their syntax to be properly interpret the questions they give you. Pseudocode examples. So here we have a set of pseudocode. What is the algorithm doing and what is the error? So if anyone wants to try this problem, pause the video right now and do this problem. Okay, here's the answer. This algorithm is counting how many of the input numbers are even and how many are odd until the user enters in 0, which ends the loop. So see right here, loop while n is not equal to 0. That means when n is equal to 0, then this loop will end. Now the error, if anyone found this, is the odds variable is not initialized. Up here, you see evens equals 0, but we don't have initializing an odd number, so you want to put odds equals 0. It's a very easy problem. There are other examples of pseudocode from the official IB syllabus, and I will link them in the description. The second type of program design is flowcharts. So IB exams won't even require you to create your own flowcharts, but they will present flowcharts to you for analysis and interpretation. And so you have to know how to recognize the symbols. And also you should just know how to do flowcharts because they are a useful tool in your own programming. So some general rules for making flowcharts. You should always format your flow from left to right or top to bottom. You should always run your return lines under your flowchart, making sure they don't overlap. Maintain consistent spacing between the symbols, and use the correct symbol for each step. So examples of this are diamond shapes for decisions, rectangles for processes, start and end shapes should be the same, etc. So here we have the symbols. The source for this is linked in the description, but basically this symbol is a terminator, which means the start or end of a program. You want to start with this, and then you want to proceed with other ones. The second one, this rectangle, is process, a task or action that needs to be performed. The arrows indicate flow, what part of the program should be executed next. So you will flow from a terminator to a decision or a process, and then end to flowing back to a terminator. And a decision, which is a diamond, is required to move. A decision is required to move forward. This could be a binary, this or that choice, or a more complex decision with multiple choices. Make sure that you capture each possible choice within your diagram. Here's an example of a flowchart. This is from the officially IB provided documents. I'll link them in the description. But this doesn't have the terminator start, but just pretend like the terminator's here. So there's going to be a start here, and it'll flow into a decision, right? And then you got here a process, which is an output, and an output here. So what this is doing is converting to pseudocode. If max is above 0, then the output should be positive, and if it's not, see it says no, it'll flow to output not positive. And it'll end here, and ideally this would flow back into a terminator. Okay, last type is trace tables. A trace table is a method of performing a manual computations on an algorithm. It is useful for error checking on simple algorithms, and on the exam you should be able to analyze and create trace tables. There's some problems related to trace tables that might appear on exam or practice problems. These can include creating a trace table to identify the error within a given algorithm, determining the number of steps in a given algorithm will be performed for a given input data, suggest changes in an algorithm that will improve efficiency. One example is using a flag to stop a search immediately when an item is found, and to justify algorithm efficiency, correctness, reliability, or flexibility. Okay, we'll run an example of a trace table. Okay, so this is an example of a trace table. So right here you'll have the algorithm. You start off with number 3, and you see this is an example right here. Your number is 3, line 1, line 2, print number. So how would you do this? You would put, since the number is 3 and you're printing it, the output is 3. So you would write 3 right here. And for this one, for I from 1 to 3, this is a for loop. So when I is equal to 1, that is the first time you're running through the loop. In the first time running, on number 4, the number would be 8, because number right here is 3, right? And number plus 5, 3 plus 5 is 8. And on your second iterate, and then you would print the number, because it says print here. Print number 8. That is step 5. And on line 6, we go through the second iteration. So when I is equal to 2, our number will be 13, because what is 8 plus 5? It's 13. And you would add that to the output, and then so on. So third iteration, 13 plus 5, 18, and output 18. So go all the way down here, and then last line is print question mark. You would just put that right there. Okay. Whoops. Okay. So here's the answer. It's pretty self-explanatory, and you basically just want to do this when you have it's a way of debugging mostly. So if you have a bug in your code and you don't know what it is, you want to run through all of your loops, run through your algorithm, and it'll help you understand your output and hopefully find the bug. Okay, thank you all everyone for watching. In our next class we'll be covering some more difficult topics, so it'll be the part 2 of topic 4, which covers standard algorithms, algorithm efficiency, and programming concepts. Out of these, standard algorithms is very important because we're learning about searching algorithms, so stay tuned for the next class. Thank you.